Hey, welcome back to Calculus. Before we start our work in Chapter 5, we're going to take a little detour back into the appendix and look at Appendix E on summation notation. You might want to look at the video for section 5.1 before watching this. I'm going to use the notation there, but it'll give you an idea of why I'm stopping in the middle of our calculus class and just giving a full video lecture on notation. Okay, but you can see our learning objectives there. I want to tell you what sigma notation is and how to use it. I won't prove, but to tell you about some properties that we'll use for this sigma notation and simplifying expressions in it. And then there are kind of four formulas, four facts that I need to know about how to sum constants, index to the first power, index squared, and index cubed. That's going to be what the kind of factual information that we're going to use in section 5.1. Okay, so let's get going. So what is sigma notation? Sigma notation is a shorthand for writing down sums. Okay, when you add real numbers, the things that you're adding together are called terms. Okay, and if you have a bunch of them, here the author has terms called AM to AN. They're real numbers, and we're going to add them together. Okay, so you can write that down, AM plus 1, and so on, and then these dots mean continue until, well, the last couple. So that sum has n minus m plus 1 terms in it, and they're called a sub i's. So the summation notation is just a shorthand for that. Okay, so I've kind of blown it up here so it's easier to see. What does the notation consist of? Well, it consists of this capital Greek letter sigma. That's the capital Greek letter sigma, and it's what tells us that we're summing. Okay, so this is just the notation that we use for it. And then we're summing some terms. Terms are the things that we're adding together. Yeah, and those terms depend on something called an index. An index is just a counter. It's a whole number, and it starts at some smallest value. That's called the lower index of the sum, and it stops at some biggest value. So you can see in the author's notation here that n has to be at least m. Yeah, it has to be bigger than or equal to it. And the index takes on every value between m and n, no skipping. So if you look up here in the picture, this first term is when the index is m, then the next value is m plus 1, the value after that is m plus 2. So when you're reading these things, this index just starts at this number, whatever it is, and then clicks up one at a time until you get to that number, and you add all the resulting terms. So that's what the summation notation means. Let's look at an example also taken from the book. I know the font here is kind of small, but in this first sum, let's look at example A together. A summing from 1 to 4. So the index is called I. It starts at 1 and it goes to 4. And the terms that we're adding are I squareds. Okay, so what does that mean? Well, when the index is a 1, then we take that 1 and we square it. When the index is a 2, we take the 2 and we square it. Whatever the index is, we're squaring it. It's the sum of the index squareds. So 1 squared, we stop at 4 because that's the upper summation. And you can check on your own that those numbers add up to 30. Okay, same thing in the second example, example B. The sum is this time starting at 3, and we're not squaring the index, we're just taking the index. So when the index is 3, the smallest value, it's 3, then one more than that, one more than that. It doesn't have a specified upper limit, an upper summation limit, so we just stop at n. The number right before n is n plus 1. It's not necessary to write this, but it sort of helps establish the pattern. All right, what are these other examples? We don't have to go through them one at a time, but here the index is called j, not I. The index can be called anything. I, j, and k are traditional. It's probably the letters I'll be using, but you can call the index anything. This index j starts at 0, and the terms are 2 to the j. So that counter is going in an exponent this time. You got 2 to the 0, 2 to the 1, 2 to the 2. Why does it stop at 2 to the 5? Because 5 was the upper limit. All right, I'll let you check that those add up to 63. Here, counter is called k, starts at 1. Where does it go? In the denominator of a fraction whose numerator is always 1. So here's the k equals 1 term, k equals 2 terms, k equals 3 term. Upper limit of integration was just unspecified to be n, so the last term you'd see is 1 over n. Notice the author didn't write the penultimate term this time. He could have. He'd have written 1 over n minus 1 would be the term right before that. All right, I'll let you look at E. It's just kind of a more elaborate. There's 2 places where the index goes. So as I starts at 1 and goes up to 3, you have to be substituting it in this formula in 2 places. So I'll let you check that those are the 3 fractions you'd get. You can check the arithmetic if you want to practice your fraction addition. I think F is worth saying something about here. The terms don't look like they depend on I. They're just 2. Well, they kind of do depend on I. They're just a constant. So no matter what the value of I is, the term you're adding is 2. Okay, so when I is 1, you take a 2. When I is 2, you take a 2. You always take a 2. And there's 4 terms because I goes from 1 to 4. So those 4 2's add up to 8. Nice. Another skill you want to kind of get a hang of is, starting with some expression that's written out like this with dot, dot, dots, and how do you write it in sigma notation? So let's take a look at something like that. So we're going to write this in sigma notation. So I'm going to make my summation sign, my handwriting version of it anyway. And then I need a counter. I'm just going to call the counter I. And where does that counter start? Well, really, I get to choose. But looking at this thing, I kind of want to start it at 2. And it looks like it goes up to a variable expression n. And what am I adding? It looks like I'm taking the counter I and I'm cubing it. So stop the video for a second and write this out. Does it produce that sum? When I is 1, I get, excuse me, when I is 2, I get 2 cubed. Yeah, that's the first term. Then the counter skips up to the next value, 3, 3 cubed, and so on. Last value is n cubed. But that's not the only way I can write that sum. I can, well, certainly change the name of the index, but that's kind of a trivial, right? J equals 2 to n is the same. But I don't even have to start at 2. I could start j at 1. If I do that, then I'll have to stop it. I can't change the number of terms in the sum. So if I start 1 earlier, I have to stop 1 earlier. And then to compensate, I have to add 1 to the thing I'm cubing. Oops, that should be a j. So check it out. If you take j to be 1, take my smallest value, well, j plus 1 is 2. So the first term in this sum would be 2 cubed. Yeah. When j is 2, 2 plus 1 is 3. The next term is 3 cubed. You go all the way to the end. When j is n minus 1 plus 1 is n. So that's going to give me the same sum. Yeah. I've just so-called re-indexed it. I've re-indexed the sum. I'm describing it with a different interval of indices. I could re-index this sum in infinitely many ways. I could write it as the sum as k goes from, we could start at 3 if you want. If we do that, we'd have to go up to n plus 1, and then I'd have to take a k minus 1 and cube it. I'll let you check that that produces the exact same terms. We can talk about this in an office hour if you want, but in general, if you decrease the starting value of an index by some amount, then you have to decrease the ending value by the same amount, but you have to increase the counter to compensate for that decrease and vice versa. All right, so that's called re-indexing. In practice, you don't ever need multiple expressions for a sum. You can use the first one that comes to you. But sometimes you have to be able to recognize, if you and your friend did this problem, you indexed it like this with I and your friend indexed it with J, you need to be able to understand that you don't disagree, that you've both got correct answers. Okay. Let's continue along. I don't want this to be too long here. There's 2 sort of important theorems in this appendix. One of them, Theorem 2, is about arithmetic properties of summations. All right, so these are actually familiar properties to you. It's just this is what they look like in summation notation. Let's look at them one at a time. The first one just says that if you have a constant factor in every term that you're adding together, you can pull that constant out. It's the distributive law. Yeah. If you have a c in every term, you can multiply c after you've added together. So that's just the distributive law. The second one is the fact that it doesn't matter how you add numbers up. If you're looking at the left-hand side, we'd be adding am plus bm plus am plus 1 plus bm plus 1, and so on. On this side, you add up all the a's, am plus 1, and so on, and then add up all the b's and add those together. Well, it doesn't matter what order you add numbers. Here it's the same. You got to be a little bit careful. A minus B. Well, as long as you have that minus sign on all the B's, then you can distribute like that too. So those are just rearrangements of the sums. Okay, I'm not going to give proofs of them, but rather just kind of mention that these are the familiar properties that you're used to when you're adding numbers. You can move numbers around, subtracting too. You just quote unquote have to take the minus sign with you. Theorem 3 is 5 special cases of what we get when we add up, kind of referring to the table of contents or the list of objectives at the beginning of the interval. What do we get when we add up a constant? Formulas for the sums of a constant, formulas for sums of the index to the first power, formulas for sums of the index to the second power or index squared, formulas for the sums of index cubed. We're going to use these things in section 5.1 when we look at this notion we're going to develop there called the definite integral. I'm not going to prove any of these things to you. I'm going to say something about A and B, and then hopefully you'll come to an office hour maybe. I'd love to talk to you about some of the ways you could prove these. The book has some nice proofs. One uses this kind of sophisticated idea called mathematical induction. But there's other ways. I mean, maybe not rigorous mathematical proofs, but we could have fun conversations about why some of these formulas are true. Let me say something about A and B, and then at least illustrate with a quick example that I'm just going to kind of squeeze in the corner down here what these formulas even mean. Okay, so first of all, A and B, what are they saying? They're saying, well, if you add the number 1 to itself, and how many times? Well, the counter starts at 1 and ends at n, so you've done it n times. Well, if you add 1 to itself n times, you get n. Okay, if you add the constant c to itself n times, you'll get c times n. All right, so that's what those formulas are saying. They're very palatable. What does c say? Let's look at an example. The sum of the indices. What if I looked at something like 1 and then I wanted to add 2? Okay, 1 plus 2 is 3, no problem. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10, and so on. But it starts getting kind of cumbersome. What if I wanted to do something like that? I wanted to add the first 100 numbers together. Well, in summation notation, I would just write that as the sum as I goes from 1 to 100 of I. Yeah, just adding the index itself. This formula C, it gives me a function in terms of n, the upper limit of the summation, so that I can compute that sum without actually summing it. Yeah, so instead of continuing on from our 10 and going, oh, 10 plus 5 is 15, plus 6 is 21, plus 7 is blah, 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 all the way to 100, I can just identify that n is 100 and use that formula. The formula says that the sum will be 100 times 101 over 2, or 5,050. All right, so if you took the time to add the numbers from 1 to 100 together individually, they'd add up to 5,050. So I call such a thing a closed formula for the sum. It gives me the sum as a function of the upper limit of the summation. And these part D and part E are the corresponding formulas for summing squares and cubes. And these things are going to be heavily used in section 5.1. All right, so when we return to section 5.1, well, and 5.2, when I introduce this definite integral, these things will be used there. So I'm going to try to keep this video short. I'm going to do 2 more examples. One is going to, sorry about the scrolling, I'm going to illustrate some of these properties in Theorem 2, how you can manipulate sums with them. And then in addition to that, I'm going to use some of the properties in Theorem 3 to write expressions in terms of the upper limit of integration. Okay, so let's do this example. I want to evaluate the sum. That is, I want to know what is a function of n, the upper limit of integration, that gives me this sum. So starting to use some of our properties. I'm going to write that first of all, I can take the sum of each one of those terms one at a time. So I have that of I squared, and then I can add to it the sum as I goes from 1 to n of 3i, and I can add to that the sum as I goes from 1 to n of 5. Okay, so that's by the Theorem 2, that you can regroup the order that you add things. This I squared is just coming along for the ride for a second, but I need to write it patiently. But this middle term, every term in that sum has a constant factor 3, so we have a property up there that says you can pull that 3 out. Likewise, I can pull 5 out of this last sum, just leaving me a 1. And now up there in Theorem 3. We can scroll back and look at for a second if you want, if you didn't write them down or you don't have your appendix with you. We have expressions in terms of n for those three quantities that I just put brackets around. Yeah, let's scroll back up and look at them for a second. We have an expression for the sum of the squares. It's this cubic polynomial, n times n plus 1, blah, 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 blah. We have an expression for the sum of the i's. And we have an expression for how to add 1 to itself n times. So we're just going to substitute those things in. All right, so this bracketed expression out front here, we should replace it with n times n plus 1 times 2n plus 1 all over 6. It's an interesting formula. It's not at all obvious why the sum of the squares is equal to that number. There's some proofs written in the appendix, and maybe you'll come talk to me about it. This 3 gets multiplied by the bracketed expression n times n plus 1 over 2. Again, an unproven in this video formula, but I'm just taking it from Theorem 3. That 5 gets multiplied by n. So the brackets are just to emphasize what I'm substituting, and I'm just going to leave it like that. I wanted to find an expression in terms of n. So now, if you gave me an n, like 100, and you said, hey, what is the sum as I goes from 1 to 100 of this? Instead of having to compute 100 numbers and then add them all together, I can just put 100 in this formula for n and compute out the value once. Okay, useful skill. Last example, we're basically going to practice the same things, but I'm going to put it in the context of taking a limit. When we get an expression for n, this bracketed thing is just like the previous example. When we're all done multiplying this out, we'll have a nice expression in n, and we're going to take the limit as n goes to infinity. All right, this will be our bread and butter back in chapter 5. So this is a good place just to practice it, I guess, as a separate skill. However, I empathize with you if you're sitting here going, why are we doing this? Why are we calculating limits of things like this? If you haven't watched the section 5.1 video yet, if you're watching them in order, that's a good question. Yeah, I agree with you. Why are we doing this? But let's do it anyway. Okay, so I'm not going to take the limit until the very end, but I am going to keep writing it on every line so that the expressions that I'm saying are equal are actually equal. So I'm going to start just by doing some algebra on my terms here before I start splitting this sum up. So I've got this 3 over n, and then I'm squaring that fraction. Well, when you square a fraction, you square its numerator and you square its denominator. Okay? So that's my first line of algebra. Again, carefully writing my limit until I take it. I also have to write this summation sign because I haven't summed yet. I'm going to multiply that 3 over n through there. So I get 3 times I squared in the numerator, and I'd get a total of n cubed in the denominator. 3 over n plus 1 is 3 over n. Cool. Now, like in the previous example, well, I'm still going to take this limit, but I'm going to push the sum through. I have a sum of those two terms, so I'm going to take the sum of the first term n cubed and add to it the sum as I goes from 1 to n of the second term. That's by Theorem 2. Rearranging the order that I add. I'm not bracketing everything here, but this limit I will if it feels ambiguous. It's the limit of that entire expression. Okay, so a couple more lines here. I've got the limit as n goes to infinity. Trying to model good notation for you. I hope that you'll take time and space to work like this as well, because it helps me keep organized. I'm doing a lot of algebraic steps, and instead of trying to do them all in a scribble corner, I'm just writing every line out one at a time so I can see exactly what I've done from line to line. Okay, so now I'm going to use the fact that, let me do it with a highlighter, 3 over n cubed is constant with respect to my index of summation. They don't change when I changes. So I can factor those guys through the sum. I can use the distributive law, right? So I'm going to do that. I've got 3 over n cubed times the sum. The only thing that depended on I in there was I squared. Yeah, can you see where we're going to use some of that information? I'm going to do the same thing over here. I've got 3 over n. It doesn't depend on I. I'm going to pull it through the sum. I just have a 1 there. Okay, so taking the limit as n goes to infinity, I've got 3 over n cubed. And then what is Theorem 2's statement about the sum of the I squareds? That's our n times n plus 1 times 2n plus 1 over 6. This 3 over n gets multiplied by n. Cool. All right, let's take the limit. I'm going to take this limit one term at a time. And how are we going to do it? Well, I'm looking at the numerator of this fraction, and I can see that it's a degree 3 polynomial in n. If I multiplied all this out, I would have an n times an n times an n. That's an n cubed. Yeah, that's an n cubed. I actually am going to write this limit sign one more time. And what's the leading term of that polynomial going to be? It's going to be 3 times 1 times 1 times 2, or 6. So that numerator is going to be 6n cubed, plus some other stuff. But remember, the leading terms dominate in a polynomial. The denominator is 6n cubed. Likewise, over here, well, 3 over n times n is 3, right? N cubes cancel, so that limit is 1 plus 3, or 4. All right, so we're going to do stuff like that a lot in section 5.1, but here I was doing it just to illustrate properties of summations. So thanks for listening.